Kirchhoff's law of voltage. The sum of the voltages around a loop must be 0. And Kirchhoff's current law is the sum of all currents entering a node is equal to the sum of all currents leaving the node. Well, basically all we're saying there is if you got 12 volts going out of a battery on the positive side, 12 volts coming in on the negative side. That's how everybody thinks about it. It's actually flowing the opposite direction.
But yes, it is. And the way that this actually is designed to be used, that's Kirchhoff's voltage law, is the voltages in must equal all of the sum of the voltage drops around it.
So one interesting thing, you can put the fuse on the negative lead and still will break the circuit because the voltage is the same.
Well, the voltage actually flows from negative to positive, but nobody thinks about it that way. And apparently we've thought about it the wrong way for so long that they're just not worried about it.
They're not going to change it.
They're not correcting
They're
it.
not going to change it. The reality is electrons flow from the minus to the plus.
So maybe that's part of the reason why you will find a fuse in both leads on a radio.
Yep.
Well, there's another reason for
faster.
that. There's another reason for that. It's because if your negative lead shorts, you got some protection. Electrons cannot be created or destroyed. Conclusion, in a DC series circuit, the current is the same through each component. So the current flowing through every one of those is the same. If it's 5 amps, it's 5 amps through every one. Parallel circuits, there is no voltage drop across a junction or node. We've covered this before, but we're just hitting it again. In a parallel circuit, the voltage is the same across all components. And in a DC series circuit, the current is the same through each component. Series is current, parallel is voltage. Okay? Oh, now we're getting into it. That's not scientific notation. Now we got sub numbers. Right. R1, RT is total, is R1 plus R2 plus R3. That's the first resistor, the second resistor, the third resistor, and however many number of resistors you got. Okay? And then resistors and inductors are the same, so if you change the R to an L, you got the same thing. And in parallel, there's a different formula. Now, how many of you want me to show you how to work out those formulas? Or would you rather just memorize the questions? You want me to physically get on the whiteboard and do the math? I could do that.
I think they have that in the book.
Okay. So if there's only 2 resistors, boom, okay, in parallel. R1 equals R1 times R2 in parentheses divided by, in parentheses, R1 plus R2. And if it's only 2 inductors, it's L. And if all resistors or inductors are the same value, our total is R divided by the number of resistors. So if we've got 3 100 ohm resistors, it's going to be, our total is the resistance divided by the number of resistors. 100 divided by, if we have 3, it's going to be 33.
And in all cases, resistors or inductors in parallel, the resistance or inductance total will be less than the smallest individual component. So that's a really good way to look at test questions.
And we're going to show you all the test questions. Yeah. Total resistance, inductance is always less than. Hey, did you read that off the screen before you told us?
What you said.
Now notice the opposite for resistors and inductors is capacitors. Okay, so it's that same formula, but opposite. So the series and the parallel uses are swapped. So you only really need to know 2 formulas and then which one applies to what. And so if only 2 capacitors, total is C1 times C2 divided by C1 plus C2. And in series, it's 1 divided by C1 plus 1 divided by C2. Do we really want to do the math? If all capacitors are the same value, it's capacitance divided by the number of capacitors. Total capacitance always less than the lowest value capacitor in series. In parallel, its total is C1 plus C2 plus C3 plus whatever in parallel, whereas it was in series for resistors and inductors. This tells us the same thing. Resistor increases, adding in series for a resistor or inductor increases the total value. For a capacitor, it decreases the total value. Voltage is added in series, currents added in a parallel circuit.
Just think of Christmas tree lights.
Whether they're series or parallel, you mean?
Yeah.
Yeah. I wouldn't worry too much about this, but there will be questions on it. Just memorize the answers. Okay, transformers. We've talked about transformers a couple of times. Turns ratio. The primary and secondary windings can have different numbers of turns and usually do. So we talked about the primary and the secondary. The one where the power's coming in is the primary, and whatever is outputting is the secondary. And there can be more than one primary, more than one secondary. The primary and secondary windings can have different numbers of turns. So you can have 100 turns and 5 turns. And what that does is it changes what's coming out. If you got 100 turns and 100 turns, you're getting the same thing coming out as you got going in, minus the inefficiencies. Turns ratio is the number primary and the number secondary. That's the ratio. The ratio of the voltage applied to the primary to the voltage appearing at the secondary is equal to the turns ratio. Oh, that makes things easy. Turns ratio is EP to ES, primary and secondary. Okay, and that's E as being the voltage. Turns ratio power output, or input, equals the power output, ignoring losses. So generally we just ignore inefficiencies, but when you're designing systems, you can't do that. But for the purposes of testing and everything, we just ignore it. It's like the isotropic antenna is theoretical, but totally impossible to build. If 120 volt AC is applied to the primary of a transformer with a turns ratio of 10 to 1, then the secondary voltage will be 12 volts, stepping down the voltage, okay? So we've got 120 coming in, and it takes 10 volts to spit one out the other side. So we get 12 volts. If we flip it over and put the voltage in the other way, and we put 120 volts in, we're going to get 1,200 volts out 10 times. But it's probably going to blow up because it probably doesn't have the wires built for that.
Yeah, the problem is that the current is an issue at that point.
Unless it was built for it.
Yeah.
It could have been built for it. You need to know that before you just flip the primary and secondary. But you can do that if it's able to hold up to your use. If a 1 amp current is flowing in the primary, then the current flowing in the secondary would be 10 amps on a 10 to 1, okay? So the current, every amp coming in, let's see, current flowing in the primary, 1 amp in the primary, you're going to get 10 times out the secondary. Okay, you're going to get less voltage, but more current. Does that make sense? Because everything's related, right? One goes up, something else got to change. Any one of EIR changes, everything else changes.
It's all interrelated.
120 volts AC times 1 amp equals 120 watts. 12 volts AC times 10 amps is the same as 1 amp at 120 volts AC. There's a reason that AC is much more friendly. I can use a lot smaller wire to carry 1 amp than I can to carry 10 amps. So we're going to do some math here on this. We'll be doing the math on a transformer, and we will do that now. Reversing the primary and secondary windings of a step-down transformer causes the secondary voltage to increase based on the transformer's ratio, and now it's a step up. But we got to make sure that we're within the current limitations of the circuitry inside. Example, reversing the primary and secondary windings of a 4 to 1 voltage step-down transformer will cause the secondary voltage to become 4 times the primary voltage. So it's 4 to 1. So if I have a primary and a secondary winding of a step down, I'm going 4 volts becomes 1, okay? It's a step down because it's a 4 to 1. So let's just make the math easy. 4 to 1 is 4 volts going into the primary, coming out as 1 volt on the secondary, but it's got 4 times as much current. But if I flip them and I put 1 volt in from the other direction at the bottom end, reverse the polarity, and 1 volt going in comes out as 4 volts with 1/4 of the current. Anybody not understand this now? You good? Anybody else? Everybody else good? Okay. The conductor of the primary winding of many step-up transformers is larger in diameter than the conductor of the secondary winding in order to accommodate the higher current of the primary. So that's the test question, and that's why if you're going to swap the secondary and the primary to make a step up, a step down, or a step down, a step up, you have to know what the current carrying capacity of coils is. Transformer can change 120 volts AC to a lower AC voltage for other uses. Shielded wires should be used to prevent coupling of unwanted signals to or from wires. So shielded is I got a conductor going through, and then I got something around it to insulate it, and I got aluminum foil usually, or copper wires intermeshed and wrapped all around that, so that anything that comes in hits that shield and goes to ground. That's on the test. And questions. What type of electrical component consists of conductive surfaces separated by an insulator? Delta is correct. How does the total current relate to the individual currents in a circuit of parallel resistors? Parallel resistors.
Charlie.
I heard a Charlie and another Charlie just right as I was hitting the button. All right. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? What causes that? Anybody?
Charlie or Delta?
Charlie or Delta. Okay, so you got rid of A and B somehow. How'd you do that?
I don't remember.
You just don't remember seeing those terms? Or?
So,
Okay. That's a valid way to eliminate. So Charlie or Delta, what's making you think it's Charlie or Delta, other than you don't recognize the other two?
guessing.
You're just...
Charlie.
Did you look it up? That's cheating.
But it sounds like it has something to do with
Okay, inductance. You got the winding, you have inductance in that winding. So then you got the two windings, it's mutual inductance. Okay, how many watts are consumed? When a current of 7 milliamps flows through a 1,250 ohm resistance. You're just ready to go do the math, aren't you?
Well, you could do this problem just with the two, the Watt's law and Ohm's law. Just
Yes.
the same.
You could, yes.
Yes.
Okay, so what's the answer?
Alpha.
Alpha.
So how did you get that with only 5 fingers?
Okay, and my brain, 7 times 7 is 49. But we got to add 6 zeros. We got to remember 6 zeros, okay?
But you only have 5 fingers.
That's okay. My brain too. So we got to add 6 zeros to our, we got to deal with 6 zeros when we get to our answer. So then 49 times 1250 is 61,225. I didn't use my 5 fingers for that.
And then you move the decimal point.
And then you got to move the decimal point 6 points to the left, which makes 61,225 into 0.06125 milliwatts. I'm sorry, yeah, it's 0.061 watts, which is 61 milliwatts. So we got lots of these questions. So shall we move on and try the next one? Okay, what is the output voltage if an input signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer? It's a 4-to-1 step-down, but we're putting the input signal is applied to the secondary. So we're going 1 to 4 now, right? So divided by or multiplied by?
Going down, aren't you?
Well,
No,
no.
we have a
What you did was you took the 4 point,
4-to-1.
yeah, and then you step down, so it's 1, right?
We're going from 4-to-1,
Yeah.
but we reverse it, so we're going from 1 to 4. So we are multiplying the input.
Yeah, by 4.
Make sense? If you reverse a step down, it's a step up. So you have to multiply that.
Yep.
Ooh, this is one of those math ones. Total resistance of a 10, a 20, and a 50 ohm resistor connected in parallel.
Remember the golden rule here. The total resistance of a parallel network will always be less than the smallest resistor.
Alpha.
Well, Bravo is smaller.
So is that,
A is 10, right? I mean, up in there.
Alpha and Bravo are both smaller than 10.
Oh, I see what you're saying.
So how do we differentiate?
The lowest number. Absurd.
The lowest number is absurd? Is that what you said?
Lowest number in the circuit.
Ah,
It's gotta be alpha.
but why is it alpha? Without doing the math. It is alpha, but why, without doing the math, is it alpha?
0.17 is too high,
Too low.
or too low.
Way too low.
that's an impossible number.
Well, it's not impossible, but it is impossible with those 3 values. Alpha, because 0.17 is too low, and the others are higher. 0.17 is crazy too low. 5.9, when the lowest is 10, is more reasonable.
So it would immediately, C and D
would work because it's higher.
They're higher, exactly.
Just throw those away.
They're higher than the lowest in a parallel. Now, if it was in a series, it would be different.
And we're gonna get there.
Approximate total resistance of a 100 and a 200 ohm resistor in parallel. 100 and 200 in parallel. What number does it have to be below? 100. Has to be below 100, right?
Yep.
Okay, so now, 75 and 67 are pretty close. Now we got to think. Now we have to do the math or memorize the answer. Is anybody doing the math?
No. Trying.
1 divided by 100 is going to be 0.01 plus 1 divided by 200. So you use that same formula there, which is also expressed right here. Parallel and resistors. When you get an answer, raise your hand. Don't shout it out. Oh, you got it? Through math or just know it?
Well, through math.
Okay, you did the math.
Yeah, I think so. If you take 1 and put it down here and divide it.
So what do you got?
You have 1 over something, you divide it by that.
And what's your answer? Okay, so. Okay, anybody else got it? You get it? You're sitting right next to him, you should have it.
Yep, that's what I got.
Okay, everybody's got it?
Is everybody getting the same answer?
You got it? What do you got?
I got 67.
Right on. Okay, that is correct.
That's right. Why is the primary winding wire of a voltage step-up transformer usually... So what's the answer?
Bravo.
Bravo, to accommodate the higher current of the primary. All right, what is the voltage output of a transformer, thinking aviation, with a 500 turn primary and a 1500 turn secondary? Now that's an easy one to do. When 120 volts AC is applied to the primary, we got 5 and 1500. That's 3 to 1. So we got a transformer, okay? And the primary is 500 turns. The secondary is 1500 turns. So what is our turns ratio?
3 to 1.
1 to 3. That's not how you express ratios, but to keep in your brains, 1 to 3. It is a 3 to 1 technically, but it's 1 turn to 3 turns. So if I got 120 volts coming in and 3 turns coming out, what do I got? 3 times or 3 times less?
120.
Do I have 3 times 120 or 120 divided by 3?
3 times 120.
So the answer is?
Alpha.
Alpha is correct. Okay, your question?
You said you have 121 and 121 out.
No.
You said?
No. It's a 1 turn and 3 turns, okay? It's the wrong way to express a ratio, but it's 1 going in and 3 coming out. So we are either multiplying or dividing by 3. 1 in and 3 out, we're multiplying. So 120 times 3 is 360. However, 120 divided by 3 is also 40. So if we turned it around, so they gave you both possible answers. They know some of you are going to go the wrong way unless you're trained. They're not trying to trick you. They're trying to see, do you understand it? So it's real simple. You got 3 times more in the secondary than in the primary. What is the equivalent capacitance of 2 5.0 nanofarad capacitors and 1 750 picofarad capacitor connected in parallel, which is the same as an inductor or a resistor in series, right? Which we just did, I believe. Same math.
Okay, so here's the theory behind that. We didn't say this earlier. When you put capacitors in parallel, you are adding to the plate surface area. That's how that works. When you put capacitors in series, you are adding to the insulation barrier. That's where the reciprocal comes in.
These questions take forever to get through if we let them do the math, don't we?
Yeah.
Just memorize it.
Well, not really. In capacitors in parallel, just add up the values.
Yeah.
It's additive in parallel.
The only tricky part about this one is nano and pico.
I don't know, I don't understand what the formula is.
So, do you have a parallel circuit?
Oh, it's just like the one on the board?
That's
They
sort
do.
of. But when it's parallel with capacitance, all the values are going together.
Okay.
It's the opposite.
Each one, okay, got it.
Remember what I told you about like units? Here's what we're going to do. 5.0 nano plus 5.0 nano plus 0.0.
Oh, you just gave me the answer.
Yes, I did. Well, 750p is exactly the same thing as 0.75 nano. So we've got 5 plus 5 plus 0.75.
Okay, anybody got the answer yet? The answer is delta. You just have,
Like units, always.
yes, like units. That's a better way of saying it than whole units, like units. What is the capacitance of 3 100 microfarad capacitors connected in series? 100 microfarad capacitors in series do what?
All identical capacitors.
In series, though.
This is serious.
This is in series.
It's not.
This is not the easy one.
So 1/100.
However, there's a saving factor here, okay? All 3 of them are identical. They're all 100 microfarad. When they're all the same value, take that value, divide by 3, or divide by the quantity. In this case, 3.
So then, it's in microfarads. Do we have to do anything with that?
No.
Why not? Because, hey, they gave us 3 100 microfarad capacitors, so we don't have to change the zeros around. So 100 divided by 3 is? Okay, so what's the answer? Charlie.
Take the easy way out whenever you can, because they're not always easy.
Okay, what's the inductance of 3 10 millihenry inductors? Well, we got 3 10 millihenries, so they're all in the same unit in parallel. Inductors.
Exactly the same question. You're dealing with reciprocal and reciprocal.
3 10 millihenries inductors in parallel are the same as capacitors in series. So it's the same method, right? So 3 10s divided by 3 is 3.3 henries, right? 3.3 henries? Don't shake your head, yes.
Charlie.
The unit is millihenries. Charlie, they put that one up on top to confuse you and get you to go, ooh, that's it. It's millihenries. Make sure you get the unit right. What is the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor? So now we're in series with inductors. We're still millihenries, so that's nice. But all the answers are in millihenries, so we can't throw any of them out just because of that. Inductors
Resistors and inductors are additive in series. No reciprocals.
and capacitors are additive in parallel.
Inductors are added to?
Say again?
Inductors added?
Yes, inductors and resistors are additive in series.
Series. Inductors and resistors in series are added.
So only capacitors are,
Capacitors are added in parallel, and vice versa. Inductors and resistors in parallel,
Are reciprocal.
and capacitors in series are reciprocal. So you only have to remember one. Just remember that inductors and resistors in series are additive. Charlie. What is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? So now we got a capacitor.
14.3.
That's where I was going with it too. Yeah, that's where I was going with it. I'm not
You
sure.
add 50 and 20?
They're different, so you have to do the reciprocals. It's capacitors, and they are in series. Capacitors in series are the formula, reciprocal formula. All you got to remember is that capacitors in series, reciprocal, you can throw out 007.
Yeah.
You can throw out 1,000, and you know it's not going to be additive because it's capacitors in series, so it has to be 14.3. But however you can remember it's 14.3 is just a whole lot easier than doing the math.
Yeah.
Just remember these questions. You're only going to get 1, maybe 2. What's the value in nanofarads of a 22,000 picofarad capacitor?
Charlie.
What's the formula for that?
You move the decimal.
You're just converting.
You're just moving the decimal in units of 3. So 0.22 is a 5 decimal move. So it can't be that. 2.2 is 4. Can't be that. 22 is 3. And 220 is 2. So which answer is it? Without remembering which one, where they are in the hierarchy, it has to move in units of 3. Has to be 22. In this, where you're just converting, it's just moving the decimal point. Okay, what is the value in microfarads of a 4,700 nanofarad capacitor? So, well, again, we're going to move in units of 3. So, can it be 47? Well, let's see. 47 would be 2 units, wouldn't it?
Right.
Going to be 0.47. That'd be 4 units. 47,000 would be 1.
1 unit.
1 unit. So 4.7, oh, hey, that's 3 units. Must be 4.7. Make sense?
That one does.
Well, I got a head shaking here. You guys okay over this side?
Yeah, it's fine.
Which of the following components should be added to a capacitor to increase the capacitance? An inductor in series, an inductor in parallel, a capacitor in parallel, or a capacitor in series? So can we throw anything out? We want to increase the capacitance of a capacitor. What can we throw out? Anything?
Probably A and B.
The inductors.
Don't those stop flow and things?
A and B aren't capacitors. We want to increase capacitance, so chuck those out. So the only real question is, do we want to put it in parallel or series to add to the capacitance? Well, Dave a minute ago told you that we're adding to the plate or we're adding to the
The insulation gap.
insulation.
Charlie.
That's my guess.
That's your guess. Pretty good guess. Which of the following components should be added to an inductor to increase the inductance? I'll bet we could throw out some capacitors, huh?
Yeah.
Okay, so let's throw out A and B again. Do we want to put it in a parallel or in series? We want to increase the inductance. I got a delta, I heard a Charlie, but we've already eliminated alpha and bravo, so it's got to be Charlie or delta, so guys, fight it out. Say again? You say Charlie? In parallel?
Inductor.
Anybody else?
I don't know if being reciprocal would be.
Own it, and if you're wrong, you'll remember.
What's your answer, sir?
Don't change your answer, because that
Charlie.
Still.
But no, it's serious.
Series.
series, because an inductor, we want to increase the inductance. We put it in series.
You are stacking windings by putting it in series. You are increasing your inductance.
Or we could think of it as a wire-wound resistor.
Yeah.
You know, if you put resistors in series, you get more resistance. Do the same thing with wire-wound inductors.
Yeah, there you go. Okay, what is the total resistance of a 10 ohm, a 20 ohm, and a 50 ohm resistor connected in parallel? Resistors in parallel.
Remember we did this a little while ago?
We did, yeah, is this a repeat?
Yeah. Well, yes, but we did it as an exercise a little while ago.
Let's say A.
Yeah.
Alpha.
Yeah,
Alpha. Because it was
So yeah, we've already had this one, so we should all know the answer is,
Alpha.
it's 1 divided by 0.17. Which of the following is an advantage of ceramic capacitors as compared to other types of capacitors? Do they have a tight tolerance, high stability, high capacitance, or relatively low cost? Ooh, everybody got that one. Which of the following is characteristic of an electrolytic capacitor?
not Bravo.
Process of elimination. So now we're left with alpha, Charlie, or delta. Think they're going to be inexpensive? Probably not, huh? No. Okay, so now we're left with alpha and Charlie, but we specifically mentioned one of them.
Charlie.
Charlie. High capacitance.
Take a battery.
Yeah, kind of. Why should wire-wound resistors not be used in RF circuits? Wire-wound resistors in RF circuits should not be used because they are?
Unpredictable.
Better.
Charlie.
Ooh, try again.
Bravo.
No, it's Bravo.
Wire-round is putting off a magnetic field, and we don't want that in our radio. Unpredictable. What determines the performance of a ferrite core at different frequencies? Hopefully we emphasize this enough. Charlie is correct. The mix. Which of the following is characteristic of low voltage ceramic capacitors?
Does this sound familiar to you?
We just had it with a red, did we have it with a red picture up there?
Ceramic equals cheap.
Depends on what you're buying, but in the matter of capacitors, absolutely. Driving by a ceramic bladed knife. It doesn't work there. All right, what happens when an inductor is operated above its self-resonant frequency? I heard a couple Charlies. Any deltas?
Yeah.
We got a delta? You should have listened to your peers. What's that?
I like it, but it's wrong.
Catastrophic failure is fun. Catastrophic success is better. Why is the polarity of applied voltages important for polarized capacitors? Incorrect polarity can cause a capacitor to short circuit. Reverse voltages can destroy it. The capacitor could overheat and explode. Are all those true? Are we sure all those are true? They are. What type of component is often used as an adjustable volume control?
Potentiometer.
Oh, spits it out. Outstanding. What electrical parameter is controlled by a potentiometer? Oh, now you got the hard part. Bravo, resistance? Do you agree, sir? Because you know what a potentiometer is, obviously, from the last answer. That's not up there. It is the resistance. That's how you control the volume. Okay. Oh, here we go. Symbols. Can we make them out? Which symbol in figure G7 represents a solid core transformer? How many transformers do we have?
Charlie.
Number 6.
What symbol is it? Oh. So
What's the answer? Is Charlie. Yeah, these are a little tough. Okay, we got another one. You tell me which one it is. What is component 1 in figure T1? Oh, this is easier. Component 1.
that one.
Alpha. What is component 2 in figure T1? Transistor.
What kind?
Oh yeah, what kind of transistor is that? Is that a FET or a bipolar?
That is,
DNP.
PNP.
No, it's not.
It isn't?
That's an NPN. Never points in.
Okay.
PNP is points in permanently. But is that an FET or a bipolar?
Bipolar.
What is the function of component 2 in figure T1? Component 2. Charlie controls the flow of current. What is component 3?
Yeah, that's a light.
That's the lamp.
Lamp.
Charlie.
Charlie. What is component 4?
Delta.
Delta, battery. What type of switch is represented by component 3?
That's a signal.
Alpha. What is component, aren't you glad we went through the hard ones earlier and now we got the easy ones? What is component 6 in figure T2? 6. There's 6. I heard Bravo. What is a capacitor? You got it right. What is component 8 in figure T2? 8. There it is.
Inductor.
Looks a little dirty right there, doesn't it?
What is that?
Is those arrows?
Those are photons. Arrows. What is that?
Delta.
Yeah.
It's a light emitting diode. What is component 9 in T2?
Oh, that's a variable.
All right. And we know it's an inductor, a resistor, because it's pointy, right? And if it was an inductor, it would be rounded corners. So it is Charlie.
And it has the little
Tap. So it's variable. What is component 4 in T2?
delta.
Delta? Transformer, correct. Which of the following is a reason to use shielded wire?
Charlie.
Shielding is to keep unwanted garbage out of our signal. What is component 3 in figure T3? Inductor. And it's an inductor because it's got the curves instead of the... component 4. What is that?
That's the antenna.
Alpha.